Okay, so I've been working on a bunch of problems, and I'd love to be able to present the solutions to those problems, but I'm not ready to do that. But I figured instead of just saying, hey, I'm not ready again, I think at least walk you through what I'm thinking and what I'm working on, and maybe that would be helpful for people who might vote questions and so on. So this is just a list of topics I'm trying that I've made, and actually they're mostly in my head, but I wrote them down this morning, so I'll show you what these lists are in a second, but they may not be complete. So first of all, over the years and previous months, but actually over the years, we've made a list of all these different things that the models in the brain have to do, and it's quite extensive and difficult. We've sort of attacked one at a time and try to figure out how to do this, like melodies or this or that and so on. But right now, I'm trying to resolve all of them. So I have a long list. I'll show you what that list looks like in a second. But I'm trying to be more like, hey, maybe we can tackle all these at once, right? That's pretty ambitious, but maybe. I've separated out hierarchical models because up to now, we've pretty much focused on what a single column can do. We've kind of pushed off on things that require multiple levels of the hierarchy. So that means the models themselves are arranged in hierarchical sets of models. And so I'm trying to deal with that now as well, which we've kind of avoided in the past, but some of the things we're trying to solve require that. I'm trying to do this in two modalities at once. I'd recommend we all think that way. So I'm thinking about it in touch and vision. And it turns out when you think about touch and vision, there are differences that are important. And so I become aware of those and say, oh, that's changes my thinking a little bit here. Another dimension that we have always tried to do is understand a single column versus multiple columns, like single column versus columns voting. And I put a question mark next to single column because I'm now beginning to think that even a single column is insufficient, that you might need several local columns next to each other at the minimum. So you can think of a spectrum of how many columns are involved or how many models are involved. We used to think it's one to many. Now I think it might be very few to many. And so that's a new thinking on my part. By the way, I should just mention, Lewis, I think there's a problem with the sensor you presented yesterday. I didn't think about it until last night, which relates to this, is that when we touch things, we actually almost always rely on multiple different pads of sensors on your skin that are not the same. And so I can talk about that, but like you slide your finger on something, the edge of your finger bumps up the things, and you might need multiple columns to detect curvature and things like that. So I had a question for you about that. Another thing I've done is try to look at, I say the toolbox of neural mechanisms. We have defined two major neural mechanisms for doing inference and model building. One is the temporal memory algorithm, and the other is the temporal pooling algorithm. These are both cellular layers. They both are useful for narrowing down and inferring. And I've been trying to understand them at a very generic level, thinking about like, and you've seen me do this, like the temporal memory algorithm can be applied to different types of data. And so just trying to, another way of sort of thinking about the solution to the modeling problem is like, well, what are the mechanisms that could allow that models to exist? And so I've been thinking about those sort of very generically, trying to understand them a little bit better. And then the thing I'm not doing that we really still need to do eventually is sort of the action policies and goal-oriented behavior as part of the models. I haven't been working on that. I've just been thinking like, okay, that's just too much. maybe I don't know, but too much. So I made a list of all these things, and I have all these ideas, and I'm trying to resolve them all at once. I'm trying to figure out what is the structure of models in the cortex that solve all these, that meets all these different constraints. And we have pieces of the answer, and we have pieces that are mysterious to us. So I'll now just sort of walk through some of these items in a little bit more detail, and then the third page I'll describe what my current thinking of solutions are. Does that make sense? Yeah. Any questions about this so far? Again, I just wrote these lists down this morning, so it's not like the list themselves, the printed words here could be, I could have easily forgotten things and not thought about them, but they're mostly in my head. I think, well, put them down on paper in my head. So let's just talk about list of model capabilities, and starting off with a single level, meaning a single column or a single level. Again, maybe it's a couple of columns next to each other. So these are just some of the things we talked about. We know we have to do inference at novel poses. That's a problem we have to solve. I also point out that, there are 2D objects and 3D objects. I'm able to infer a circle and a sphere, and the mental logo is 2D, and yet the coffee cup is 3D. So this is an interesting dilemma that, like, how does the system deal with both of those? Then lately, I've come to think about it as objects defined by morphology. So these are objects where there's continuous surfaces, but there's no salient points, right? So there's no point you can say, oh, there's a feature here and a feature there. There's typical examples: a circle and a cylinder. I've talked about a bunch of these recently, how we can recognize them, how we can learn them. It really is, it forces you to think, it made me think, like, oh my God, you can't really just say there's these features that it's figuring out the displacement between them. Then there are clearly objects that are defined by features at some relative displacement. For example, a word. A word is a set of letters in a certain arrangement. That's it. There's nothing else to it. There's no necessarily morphology to the word. It's that arrangement in a certain order. If you change the order, you get a different word. Another example would be a bicycle, which is basically composed of wheels and frame and pedals and things like that. And then I've been asking myself, can they be the same? I'd like them to be the same. That is, I'd like them to be 2 points on a spectrum. And that is what I'm working on right now. Can the same mechanism do both? And when I talk about the solutions, that's my current approach. I'd rather not say, oh, there's these 2 types of objects. And I talked about here on the whiteboard saying that, but I don't think I'd rather not that be the case. I'd rather it be somehow we just have this continuous mechanism. And in some sense, I'll get to it when we get to the solution stuff. Another thing that we have to deal with is changes in scale. And there's multiple ways this can happen. There's changes in absolute scale. So imagine I have this coffee cup, and now I have a little miniature version of it. Well, I recommend the exact same thing, but at different scales, and I would be able to manipulate the smaller one just like I'd manipulate the bigger one. I have no problems with that at all. I'd say, yes, I know it's smaller, but I would notice it's the same thing. But then there's other changes in scale. Like in vision, you can get change in scale with perspective. We saw that with the picture of the truck that Heiko put the other day. On the retina, the rear of the truck is small, the front of the truck is big. That's a different type of change in scale that doesn't occur in touch, but it does occur in vision. So that's an interesting question. Then there's changes in scale that are not like absolute. You can take an object and stretch it. So I can say, oh, imagine if this is a fatter version of this, same height but fatter. I can easily imagine that, and I can learn that. And then I would somehow be able to take my model of this cup and stretch it in 1 dimension. So that's kind of a weird thing. We'll come back to that again. So scale is not a singular thing, right? There's various weirdnesses about scale going on. Then there's a distinction between static objects and changing objects. Changing objects, sometimes I refer to as behaviors of objects. And so objects, it's easier to think about a static object, never changes. But we do have objects that change in morphology. That is the actual objects themselves can change its shape. The stapler is a perfect example of that. There are other ones. There's plenty of examples of things changing their shape in their arrangement of their features. And then some are changes in features. Like you can say, okay, the morphology object changed, but the features stay the same. Or you can have the morphology object stay the same and the features change. Like the icons on the display of your phone. So that's kind of weird. And then there's a spectrum of these changes. The very predictable ones, like the stapler, it only has a certain set of behaviors. It's always the same. It's fixed. We can learn those. And then there's unpredictable ones. The one we've been talking a lot about, like t-shirt. A t-shirt has a shape. You can imagine what a t-shirt looks like, but half the time it's in a pile on your floor or something like that, all plunged up net. We're still able to manipulate that and work with it. It's the same t-shirt. We don't get confused and say, oh, that's something different as a pile on the floor. So there's a spectrum of morphological changes and changes that can occur on objects. And then, of course, we were able to infer and represent the object state. So it's, when I see the stapler open or close with different icon on display, I know that, and somehow there's a state to that object. And I say, yes, the stapler is open. And how do I represent it? If I have a model of an object in one form, how do I impose that state on that? And is the state saying, no, the stapler is normally closed, but now there's a state where it's open? I mean, it's kind of a weird stuff going on there, but to figure this stuff out. Then one time I talked about class versus specific instances. So that's another problem we have to deal with. What's a cup versus my cup? what's a cat versus a tabby versus my cat, right? These are all scales of on a spectrum of classification and inference. And we seem to be able to do that pretty well. You know, we can represent specific things, classes of things, and the class of things can be broad or narrow. We can have different labels on different levels of the class. So that's another weird one. Yeah.
In that case, you're considering one specific object to belong to remaining classes, right? So your cat would be a cat and your cat. So it's just two different classes and the object belongs to.
All the words made sense, but I didn't understand the original question.
Yeah, my question is, are you thinking of different classes? Like there is my cat and there is cat.
Well, I wasn't thinking of different classes. I don't know what the right word to put on it is.
I think that people call it like an ontology.
Okay.
Like, you have animals, cats, and then my cat.
Yeah.
That kind of.
And even my cat,
feline,
there seems to be this spectrum. You can sort of break off pieces along the way and say, hey, it's got the same set of features, but the arrangement is slightly stretched. That's one thing. Or you could say it's the same exact morphology, but different set of features, or some combination of those. And you can put labels on, and so you can say, yes, that's a tabby versus a, Siamese cat or whatever. But then you can also say, that's my tabby cat. It's like, faces. So I guess all I'm saying is there's a continuum of labeling abilities, right? And I don't know if my cat is a specific, there's a special version of that one unique thing. I think just seems to be a spectrum of similarities, and we can label those. So it's not like somehow my brain is able to put different labels on different parts of the spectrum of shapes and features. It's a surprising thing that you can do that. It might be easier to say, oh yeah, we're going to just do like one classification or two, but it seems to be multiple ones. I don't know. These are open, some of these are not really clear how you specify this, but it seems we're able to do this. So,
Well, WordNet kind of does that for every English word, basically, or all common English words, creates like this hierarchy. It doesn't have, your cat or my dog or whatever. It doesn't have that level, but everything about that is.
But that's based on semantic versions of words.
Yeah.
This is based on physical structure of some object in the world,
Okay.
right? So it's maybe they're achieving a similar kind of result, but they're on very.
That one is semantics.
Yeah. This is very different. Now you could just look at statistically usage of words in the world and make that connection, right?
No, I think it's semantics.
Yeah, but the semantics come.
It's not shape-based.
No, but the semantics come from word usage, right? Where does it appear? No one sits there and codes down what it means.
No. This is hand done. Yeah.
Okay. Well, fine. I don't. That's not what I'm talking about here.
Yeah.
Here we're learning a model through sensory motor inference, right? Or sensory motor modeling. We're touching something. We're seeing something. We're building a model of it. I need to classify that model. I need to do inference. I need to do inference at novel poses, and I'm somehow able to do inference at different levels of. I can put a label on different changes in that concept. There's again the changes in morphology, changes in size, and changes in feature sets, and those seem to be the three things you could do, and we're able to pick off pieces and label
them. Yeah, the only reason I brought this up is that the graph matching algorithm we're developing should be able to handle those. Like it's never going to match one thing. Each one object has to be several things. So we can't return a single.
Each one object has to be several things. Like why is that?
Well, the cat's going to be an animal, the cat's going to be a cat, and the cat's going to be tabby.
But couldn't I just say this is a coffee cup and be done with it? Does it have to be something else?
Well, there is, like I said, there is your coffee cup. There is.
Well, maybe not. Maybe
it's both.
Maybe. I don't know. Okay, fine. I guess I wasn't enforcing that it had to be multiple things. I'm just saying it's capable of doing multiple things.
Right.
So the problem I get is when I think about how neurons do this, our classification is the temporal pooler layer, right? That's that's at least where we form a stable representation for an object. And so you can classify that pretty easily, but it'd be very difficult to classify that temporal pooling cellular pattern in. You could associate different classes, but it's just complicated in the brain. Maybe it's easy in the method you're using. So again, I'm kind of thinking about this in brain mechanisms. So maybe you've got a solution to that. That's fine. But anyway, it's something I think about, like, you know, it gets back to this whole issue that objects are stretchable and morphologically changeable, and the feature sets can mix and match, and yet you still have a model that works for all of them, right? It's like you can say, yes, that is a feline animal, but it could be a tiger or a cat or, you know, something else. You know, who knows?
Lucas, was your original point that it's not just one thing belongs to multiple levels of the same hierarchy, but that you can kind of have different group by operations? So like a cat is, yes, it's my cat, it's a feline, it's an mammal, but it's also like, okay, what are things that are fuzzy? Okay, like Jeff's jacket, my cat, a stuffed animal, and so on.
Multiple hierarchies is what you're saying.
Yeah, I guess that's what I'm asking.
Not just hierarchies, I think even horizontal, that gets back to the point we discussed a month ago, that there is no one class for anything, and it's just not on a hierarchical level, like a car.
I agree with that. There's a spectrum of patterns that represent this thing you're observing, and you can assign some subset of those patterns to some label.
Yeah, exactly.
Yeah.
And they're good associations.
Yeah, but it's interesting because if you think about the representational structure that you're dealing with in the brain, that representational structure, you know, you have to be able to do that somehow. I mean, it may not be hard. It's just a thing that has to be done, right? So I didn't say these are all unsolved. I just said these are things we need to do. Right, so that's a good point. I mean, I haven't been thinking about this particular point too much, but I've been sort of in your category, Lucas. It's like, well, I'll just be able to associate this with different labels, but I have to have flexibility, right? What qualifies as a tiger is also quite flexible. So there's a range that's a tiger, and there's a range that's cat, and there's a range that's, you know, wild animal. I don't know, there's a whole bunch of stuff that you could do. So maybe this is not a hard one. I don't know. I just put it in there. We haven't really spent a lot of time talking about hierarchical models. At Numenta, we've tried to avoid that. We've tried to say, let's stick to a single learning column at a time. But I'm trying to think about that more right now. And even then, it's really kind of interesting, weird actually. So I'm thinking like, okay, what is a hierarchical model? A hierarchical model is you've got basically some object models that are now part of a bigger object model, right? And you can break them down to different types. So here's an interesting one where I have a morphological model on top of a morphological model. So this is like a coffee cup with just a circle on it, right? The circle is a morphological model, and the cylinder is a morphological model. So there's no features in any of these things, yet I'm able to place a circle on the cup. Okay, that's interesting. So I can't rely, I have to be able to accommodate that. Then you can have features on morphology. That's a classic example of the logo on the cup. Well, the logo consists of individual features ranged to each other. And now I can place that arrangement on the cup. So I don't know if you understand why these are bothersome to me, because if I'm thinking about morphology and features as sort of separate things, then it gets complicated how you do all these things. And then you can have features on features. For example, feature models. So the letters, you think a letter as an object, it could be in a word, and the word can be in the logo. So you have, these are just relative arrangements of pieces and relative arrangements of relative range of features. And other than the letter itself, it's not morphological. It's just like, it's like displacement of features. And then there's another interesting question. It seems like we can go very deep hierarchically in these compositional models. And we talked about this even in, I think, framework paper, like they could be recursive. But you have to be able to do this in a finite number of levels in a hierarchy. So I can imagine like, okay, a bicycle's got a wheel, and the wheel's got a tire, and the tire has a stem, and the stem has a screw hole, and the screw hole has a valve, and the valve has a little piston I push on it. And so there's a lot of levels to that hierarchical composition, but I can't rely on n levels in a hierarchy in the brain to do that. This aren't enough, and that's not how it's going to work. So somehow the mechanism have to accommodate, sort of recursively, like drilling down within the same set of neurons, somehow and not get lost. That's the best I can describe it.
Regarding the features and features, the letter example, I would recognize, consider letter to be a morphology.
Yes, I did say that. I said letters are morphological features, but now it's an object. So now I have this object called a letter, and the arrangement of the letter is features relative to each other. And then the arrangement of the word Memento relative to the triangle of logo thing is also features to features. So it was more like, it was like letters. It was like, I was just trying to show that the letters are arranged in a certain way, and then the word is arranged relative to the components of the logo in a certain way.
Like the discussion we had 2 weeks ago, we were thinking along the line that a feature is actually more like a pixel color of a specific point.
We have to be careful getting features, yeah, that may be a different use of the word I'm using here.
Yeah.
In a moment, I wasn't trying to be careful about here. What I meant here was, well, you'll see in a moment, what I think a feature is just another object. So that would be a way of putting this. You could say objects on objects. So letters are objects, and then a word is an object. So you have letters on objects, and then logo is another object, and so on. I think I'm going to get away from using word features at all in the future.
Could I just do a little pushback on that? Because you keep saying that a circle has no features.
It has no, what was the word I used up there? Continuous surfaces, no salient points. That's what the word I used there.
But they have boundaries. Those are salient.
Well, they're not specific. A salient in my means it's different than the rest. Salient means this thing is more interesting. This is how it's typically used. This thing is more interesting than the other things around it. In this case, there's nothing more interesting about one part of the circle than the other part of the circle. There's nothing to direct you to one point to say this thing is the thing I want to pay attention to.
Right, but that's a description nonetheless.
I'm just saying there's no salient points.
Okay. So nothing you can fasten on, but
I didn't say there's no features. I said there's no salient points.
okay.
Obviously, we talked about the solution of this as being a continuous feature of curvature, and we'll get to that in a second.
Mhm.
But the point was, when I first started thinking, we first started thinking about building models using displacement, it was always this thing here, this object is at this location, and this object is that location. We can calculate the displacement between them. And there's a lot of things in the world that just don't have that.
I understand your distinction.
Yeah.
If that's how you're trying to represent it.
Yeah. There's no points in which you could say, this is the thing I want to calculate my displacement from. That's what that means, no salient points. So you could randomly pick points, but that's not going to work. So we don't want to do that. That's what led the whole discussion about it has to come down to local curvature at any point, and then learning that continuously so that you have a continuous representation of the feature space in some sense, as opposed to a punctuated or a representation of feature space.
Okay.
That just forced you to think about that all the time. Touch and vision. I mentioned earlier, there are differences. I've always pretended there aren't. Yeah, so let's do it. It works in both cases, but it's not really true. Vision has, when you actually see things, it has a scale that changes with perspective, and that doesn't happen with touch. So that's a difference, and there's going to be neural mechanisms that deal with that difference. When you touch something, you know exactly where your finger is. Let's say, pretend you do. But the thing you're touching doesn't change in scale based on how far away you move, right? So you know the depth, but you don't have to infer that from scale, and the scale doesn't change as for the way it is. So
Regarding the interplay between vision and touch and the scale. For example, if I look at the cast down there, I can imagine picking that up with my fingertips.
Yeah.
And when I near the car, it's like I can imagine touching the whole side.
But you aren't actually fooled. You don't think that's a teeny little car. You know it's a big car, and it's there's an optical illusion. When you look at things on the horizon, you're very bad at judging the size of them. You think the moon is really big. If I look at a ship across the harbor, it looks bigger than it actually is, and you just can't shake this. It's sort of like maybe like the what columns in your brain are saying, I know what this model is, and I'm not really, I'm doing it independent of scale right now. The model's like, and so that it sort of separates the perception of what actually is. It's related to that problem. But I don't think it was a small ship, right? I don't think it was the moon as being teeny. Anyway, it's an interesting problem.
In the neural mechanisms, what about the voting layer?
That's the temporal puller. I included that in that. The temporal puller
okay.
is
Okay.
fact, that is the main method by which it does inference, in my mind. I mean, you can narrow it down by passing in a series of sparse representations, but its inference power really comes from voting with other columns.
Yeah.
So I just included that there.
Okay. And the spatial pooler then?
Well, the spatial pool is included with temporal memory.
What about the,
I just viewed it as two cellular layers, okay?
Right.
So there's a cellular layer we call temporal memory, which includes the spatial pooler, and there's a temporal pooler, which includes voting. So
what about attention? Are we doing attention?
good point. Really good
Well,
point.
to spatial pooler.
Oh, yeah, I'm sorry. I just thought that those were.
With attention, we don't have a
No.
neural mechanism, at least in our papers.
Yeah, we don't have no mechanism for it, but it is, I would put that under,
Columns.
it needs to go somewhere in here. How about we can just say, how about that?
How about knowledge transfer?
You could argue, I don't think of that as a separate thing. That to me comes up under, okay, we could do that. Yeah, it's another thing I didn't list here. I guess
would that be a neural mechanism or would that be a property somewhere else?
Yeah, I'm thinking
Maybe in the
property.
hierarchy.
Yeah. I think that is, I just haven't, it's in my head when I think about learning. So
Yeah.
I didn't
I had
have
a
that.
question about that, like, what about like short-term memory and learning, and that's not anywhere here.
Well, I think the short-term memory is not issue I'm not particularly concerned about.
With learning,
Well,
continual learning?
yeah, sure. I mean, I guess there's an assumption under all of this for learning through movement, right?
No, but I mean specifically being able to learn things quickly.
I just assume that, I guess that's an assumption. I didn't break it out because I'm assuming that's basically
That's
how.
like the hard thing with deep learning.
Well, for us, learning quickly is not hard, right? We form synapses quickly, right?
Humans do, yeah.
Yeah, and all of our neural mechanisms can learn quickly, right? We've never introduced thought of any neural mechanisms that couldn't learn quickly. So that's not a hard problem for us, I don't think, at all. I mean,
But shouldn't it be in here?
well, I assumed it's okay, fine. I guess it wasn't a problem I'm trying to solve because I think we don't have that problem.
There's two aspects of learning quickly. You learn very few observations, but you don't learn fast mechanisms. We don't need to worry so much.
This is few observations.
Right.
And I guess I didn't see that as a problem for me to think about because nothing we've done actually is, everything we've done is already fast learning. A few observations. The whole Dendrite's property and the way sparse distributed memory works is it just comes from the There's nothing we have to do that. Backprop has problems with that, but none of the mechanisms we've considered has a problem with that. As long as you can form synapses quickly, you're done. Right? There's no settling, there's no multiple passes and nothing. All these mechanisms could do one shot in it. So I would just say easy with dendrites and other stuff. So again, I'm not worried about that.
What about senses other than touch and vision?
No, I'm not worried about that either. First of all, the other senses are not nearly as interesting, and I think there's very diminished benefit from adding more. I think a little bit about audition at times, because audition has some of the capabilities that we have with touch or vision. You can locate a sound, but you really can't. There's some limitations to that. And it's really relying on temporal patterns, which we do automatic. I didn't put that in here. I could have put in, learning sequences, because I think that's part of the whole thing. I just didn't put it in because the way I look at it is a temporal memory algorithm can do both. It can learn sensory motor inference, and if things repeat in time, it will learn sequences. It just comes for free, so I didn't have to put that in here.
What about an airborne molecular analyzer to I mean, that appeals to me like with the coffee example because.
So we're trying to get at core fundamental learning things, right? And so anytime I think about another sense or smell or touch or whatever, it's under sound or taste, you have to ask, is it going to add anything fundamental to the algorithms here? This is not a practical exercise trying to figure out, oh, how would I implement, an aroma tester, right? This is like more like getting at the fundamental base mathematical principle by which models are built. And then I could throw in, color and tonal qualities and chemical sensors and a whole bunch of other stuff as this sort of, oh yeah, I can add these other sort of attributes to the system, but I don't need to worry about any particular one.
Okay.
And I think in some sense, I think some of those are not getting at the core essence. Again, think about vision. You can see pretty well in black and white, right? Color adds, but it's not really essential for a vast majority of what we do. So it's not like, oh, I have to have color, I can't understand vision. That's not true. Not true at all. So then you have to ask, what are you adding for that? So I kind of put in a little category for the side, like, yeah, we could add these sort of, some sense, important but not essential components to inference. I could add a color to something and say, well, I can distinguish between your cup and my cup by color. That would be, yes, I should be able to do that. But I just put that in the category of there are other sense things that are not necessarily spatial or morphological in some sense. Anyway, that's how I view that. I could, again, you have to. This is already a huge list of things to deal with simultaneously. So I'm still making some choices.
Right. One way to look at it, Greg, is what is the reduced set of senses that someone could have to build a workable world? So Helen Keller with a little bit of pre-learning because she lost her vision and sight. Wasn't at birth; it was a little bit after that. But she built a whole model of the world just on the pure touch.
She was very young when she lost it, wasn't she?
She was young, but she had enough. I mean, the key thing in there was that she had learned the word "wa" for water, and then she finally made the connection.
Yeah. Well, okay, that's she was pretty primitive. She wasn't like she had real language.
No, I understand that. So it wasn't like.
But she had several months of vision.
Yeah, I think she did. She had an audition too.
I mean, her big thing was actually that her epiphany moment was that there are words that represent things in the world.
And that the person was trying to
do that. It took a long time before she realized that there's actually a pattern that represents this thing and another pattern that represents that thing. So her language ability was very, very small. I think you can just say pretty much she was close to born without any of these things, but maybe it was the borderline.
But you could say, someone who was born blind or with one eye doesn't need that type of depth perception.
People who are born blind completely get along, they have deficits, but their model of the world is pretty good.
Yeah. It's a workable model.
Oh, it's really workable. They just can't always infer the right thing, right? Because they can't infer at a distance other than through hearing. So I think Kevin's point is a good one, though. It's like I'm not trying to build a minimal set for a workable thing. I'm trying to get at the core essence of model building. So it doesn't mean that vision and touch are the things I care the most about. Those are just two that are really pretty important and self-sufficient and gives us sort of an ability to look at the two things. Already I can start seeing there's differences between them, and it's important to understand like the core components of the model building can't rely on what something vision has versus something touch has. The core components have to be the same in both cases. That makes sense?
Yes.
Yeah. I talked about hierarchical model, touch and vision. Again, I just went briefly about the single column thing. I realized when you touch something, I always talk about, oh, there's a single column getting this input, but that's not actually what happens when you touch things. Because if you run your finger along a surface, what happens is you bump up against something like this lip here, And I'm not sensing that with the same part of my finger. I'm sensing of a different part of my finger. It's like it's a different part of my sensory organ is saying, hey, there's something over here. And so that's one of the first clues. You know, it's not like I have this one little patch that's moving over everything. It's like I have this patch that's moving, and then all of a sudden other patches kick in and hit things. And that seems to really, I try to do inference of imagining just your finger, never, you know, one little thing. It's really hard to do that. And even when you grab something like this, I don't grab it with the pads of my fingers. You know, this was touching this, and this was touching this. And so it's not like I have this perfect, you know, thing like the kind of sensor Lewis was talking yesterday. I can always tip it orthogonally. I sort of sense a bunch of things at different points, at different parts, and each one's reporting like, oh, I'm sensing a border here, but it's not the same patch, right? Another thing is this whole idea of detecting curvature, which is really problematic, but it's not problematic if you assume that you have multiple patches sensing at the same time. And, you know, so like, you know, when I'm touching this edge of my cup here, or if I touch the edge of this whiteboard, there are multiple patches on my skin getting input. And so I don't have to have a single sensor patch saying I've detected an edge. I could rely on the fact that there's several in a row, and those together are sort of voting on an edge. So that is, you know, that's a big change from my thinking in the past. And it's not, and sometimes I like it. It basically just says that inference is on a scale. We used to think the scale was 1 to many. I now think it may be a few to many. And in some ways that's nicer. Certainly, it's just a different way of thinking about it. So I'm willing to accept that as a premise now. I talked about the different mechanisms, and I don't really haven't talked much about action policy and goal over here. I mentioned that already. So this is like the list of things I got in my head plus more that I just couldn't think of right now. And trying to resolve all these things at once, it's, you know, it's kind of hard. So some of the solution ideas I'm working about, you've heard of all these already, so I just thought I'd go through them, just make them a little explicitly. I'm working on the idea that one mechanism could do both morphology and feature displacements. That is, I've talked at times, maybe there's two mechanisms, like here's a morphological model, and here's a feature displacement model. But the thinking about the you know, the circle and the sphere and the oval and things like that, made me really question that idea. So in this idea, you could say like morphology is just defined by curvature, which is just a local displacement. It's an instantaneous displacement at some point. And then we would store, just if I move my finger around a morphological object, I'm storing, continuously storing sort of displacements, which is continuously storing the curvature at that point. And I think that can all need to work with reasonable amounts of memory. I haven't worked through the details of it yet, but I think that can work. And then you could vote and all those things would work. Then the second problem comes about, which is I'm trying to figure out the displacement, for example, between, you know, on this table between my mouse and the coffee cup. This actually might be even harder because where's the location of my coffee cup? It's not one thing. It's not one place. You know, do we pick the centroid or the, you know, I don't like that idea. You know, the original solution you have for displacements in the framework paper didn't rely on that kind of thing. It was just, you know, it just didn't require that sort of point, the point.
Yeah, that's what is my, doesn't the frameworks and columns plus stuff do that?
But it didn't work. It didn't work.
The only reason it didn't work was because we didn't have the reference rate explanation.
Yeah, and
but now we have a handle on that.
Well, it didn't. Well, it wasn't just that. We could never get it to work. Even thinking reference frames, I could never get it to work. We were using multiple grid cell modules for that, right? And derivatives of multiple grid cell modules. Yeah. Well, now we're not looking at multiple grid cell modules anymore. So that mechanism, I'm not doing.
Right, the mechanism might not be, but that it still did that.
And it didn't do orientation.
That's just the reference frame.
Well, okay. I don't know if we could have gotten it to work with grid cells with reference frames.
It should be.
Well, I'm not sure. When we worked on it, I brought that issue up and we just could not get it to work. Maybe you can tell me how to do that. And then it was also the issue of the curvature of the cup. It didn't do that.
It didn't do continuous shapes.
Yeah. So there was we did it. It was beautiful actually, but it didn't solve all the problems. And we knew that in the paper. We brought it up in the paper, and now we've moved away from these multiple grid cell modules. Therefore, we moved away from the multiple displacement cell modules. So we have some parts of it there. So I think that's a really interesting, it was really, that's a good lesson. It's like, oh, there's some really clever things about it. That's why I brought it up, right? I brought it up because it's tempting to say, what's the displacement between these objects? You can just point to here's a point and here's a point and calculate the displacement. It doesn't seem to be that's what we're doing. It's more like we did in the frameworks paper, but somehow different, right? The frameworks paper didn't work completely. Yeah, it's got to be more like that. So I'm just pointing out, I now feel more comfortable doing the continuous displacement than I do doing the point-to-point displacement, because I don't know how to do that. So I'm working on that, right? Anyway, in terms of morphology, the temporal memory mechanism, we've talked about this. It can do this. It can learn continuous displacements, and it can, as with in sequence, like in the sequence memory, like a melody, it can do point-to-point in some sense. So it's close. I just haven't gotten all the pieces to work yet. Really, the hard thing I'm struggling with is this issue of where's the location of this object? Where's the location of this object? And it feels like it needs to be more like we did in the frameworks paper, but I don't know how to do that. I don't know how to do that, especially since we're not using multiple grid cell modules.
Why would we decide not to use grid cell modules?
Because there was all this evidence to suggest that was wrong.
That's a good
It required quite a few grid cell modules, right? Because you're going to create an SDR across multiple grid cell modules, and therefore you had to have this, let's say we need a minimum of 10 bits or 15 bits to form a dendrite to recognize a pattern. Then you have to have at least 15 of these grid cell modules, and they don't exist. And the grid cell modules in the entoronic cortex are stretched out, they don't seem to communicate with each other, and they're very different.
That's a pinwheel thing.
What's that?
The pinwheel, you don't. There was a pinwheel.
Pinwheel?
Pinwheel.
Pinwheel, the tank paper.
Oh, not the tank paper.
But there was some kind of central.
That was in the V1 model. Right. Anyway, it doesn't appear that at the moment, it doesn't appear that there are multiple grid cell modules in a single column or even in multiple columns near each other. And there doesn't appear to be enough grid cell modules, even if I allow myself to look at neighbors and other things. It just doesn't. I could be wrong. All right. But at the moment, and as I pointed out before, there's other ways of achieving the same result. You could feed in, if you think about the tank paper, which showed what a grid cell module looked like in a planar view of entoronic cortex. And it was composed of 6 phase groups, and about total, they're about the size of a quarter of a column. So you can say, okay, maybe the quarter of a column, the grid cell module looks like that. It's got these multiple phase clusters, each representing the bump. And now in each one of those would actually be a mini column. And if I use the temporal memory on that, I could form a very unique representation of space, not by using multiple grid cell modules, but by using a mini column of cell active in each of those, right? So imagine that the mini columns of the temporal memory are not features; they are the location, the grid cell locations in each of those, in all those phase clusters. That actually fits really well and looks beautiful, and there's evidence to support that idea. So that's a different alternate view of how you get to a unique location using grid cells without using multiple grid cell modules. And that to me is now clearer and cleaner and probably more likely if it's doing that. If we need to get unique locations, that seems to be the better way to do it.
But that sounds like the same mechanism.
No, it's not. I don't know if people online can see this.
Sorry, I don't know what a tangent.
You need to get the wet papers in here to wipe this off. The way we did it in the framework paper is that we assumed that there were multiple grid cell modules, lots of them, and you had a bump of activity in each one, and these modules had to be different. They either had to have a slightly different scale, or they have to be a slightly different orientation to each other. So the bumps don't move in unison, they kind of move around. And if you sample across them, so if each one gets anchored independently, so I'm on an object, the coffee cup, and each one gets anchored independently on that coffee cup, then the combination of these guys would be unique.
Right.
And as you move around, it continues to be unique. It's this very, very large space. The alternate proposal is that a grid cell module is actually like a temporal memory, and it's actually a layer of cells. It's a layer of cells, and these cells here really represent our mini cones. And so you have a bump of activity going along in the mini cone space, and yet you're picking individual cells in here. And so this is much closer to this is the temporal memory algorithm where you're applying grid cell input versus feature input. And in this case, you'd end up with very unique representations of each location. And then you could, just like in the temporal memory, you could define a space of this object where all the points are unique, right? But you still get you would still get the path integration at the mini column level. And in the tank paper and other papers, what we found, what they pointed out was individual grid cells often would not fire when you expected them to fire. And they did so reliably in a particular context. Now, I would have preferred to see it very sparse. They didn't report very sparse, but they did say individual cells would say, I expect that cell to be firing because the bump is here, and that cell is not firing. And it does so always in this context reliably. So it's not some random thing or error. So that's evidence that at least moving in this might be possible. And then I talked to Tank, I think, about when he did his, he does this, they did this with this photo technique, right, where they can look down in the active cells. And that photo technique actually looks at a very, very narrow layer. It doesn't look at the depth at all. And so they wouldn't see the activity of these cells down here. So anyway, that would be my current hypothesis, better than this one, because there's a lot of things wrong with this one, and there's no evidence for this.
Okay.
So like the duck analogy, it's going along, but underneath it's paddling furiously with all those things that they can't observe.
I guess I hadn't heard of the duck analogy, but yes, that would be like the duck analogy.
It looks like it's smooth, but it's real.
It's more like the duck's feet are just little pieces of them, it's not a complete foot.
If the duck was an SDR, then
Yeah.
Okay, jellyfish.
So this is how I get, this is I went back to sort of the basic neural mechanisms, like the temporal memory mechanism, as soon as includes the spatial pooler. In this case, I wouldn't have a spatial pooler here. I have something that's equivalent to the spatial pooler. The spatial pooler takes like some sensory input and it turns into a sparse, or not too sparse, but some sparse representation mini columns. Here, I already have the grid cell is already a somewhat sparse representation of space. And if I just assumed that the mini column was actually representing and I don't need a spatial pooler. It's just substitute the bump for the spatial pooler with the bump for this stuff.
So right, stable.
And then yet the same mechanism says, you give me something that's not unique, it's sort of measurable, in some senses it's measurable because it's path integration. You give me something that's not unique, I will form a unique representation for it. And now I can associate this non-unique bump with a unique location on the coffee cup all the time, and nothing else is going to be in the same space. It also gets around the whole issue of the grid cells repeated, right? Because essentially the mini column space, you can only represent a small number of things, and they have to repeat. But in the cellular space underneath it, it's a very, very, very large space, and they're not going to repeat. So I think I talked to Ben and B about this recently, maybe someone else, I don't know. But I think that's a reasonable part of my toolbox right now. That's the thing, assume that. And so what I'm actually thinking about, okay, there might be multiple cellular layers in a column that are working on these principles. We talked about one could be like taking displacements as your sort of input, meaning like equivalent to the output of the spatial pool or equivalent to grid cells. And the displacement says, okay, here's a displacement, but I can also represent that displacement uniquely in the context of this particular object at this particular location. And therefore, in the context of the coffee cup, I know that if I have this displacement in the context of the coffee cup, I go this way, I'll have something else. But in a different context, it would be a different thing, right? So you go from like, I'm measuring displacements, but I need to represent them uniquely in the object space, or uniquely for the object. So, okay, let's keep going. So the solution ideas. I already mentioned this one, that I'm trying to get it to that there really no distinction between morphology and feature displacements. It's one way to think about this. Imagine you're a primary column and you're getting input from a sensor. And I've always said that, you know, this thing you're getting in, you can't really subdivide it. It's like imagine all the axons get mixed up on the way up here. So you really, you know, it's not, you don't really can't, it's not like you can't detect pattern in here, but they're just sort of spatial. They're spatialist. They're just patterns. And so imagine this. This is your input coming into this column. This is the thing we detect, what we might call a feature. And then ultimately, you're going to do temporal pooling because we're going to have a stable representation of the object. That's the whole goal of the inference here. You're moving, touching, and then you have this changing input coming in here, and then you have a stable representation of the label of this object. Right? This is why the world seems stable and your eyes are moving. This is why when I move my fingers like this, I don't think the laptop is moving. So that's like the core essence of inference is multiple inputs get mapped to single or a more stable output. In this case, the input I'm getting could only be what's coming from the sensor, which is kind of impoverished. So let's say I'm going to call that. I'll just say maybe I can detect a curvature. And that's the only thing I can get to work with here, or curvature plus color and other things. I'm not going to talk about that. But now I have another column, which is somewhere else, and it's getting the output of this guy as its input, right? Now, this is a limited number of things I can detect in the sensor. The sensor can't detect thousands of things. It's just going to say, you know, curvature this way, curvature this way, curvature this way. But the output of this thing can be quite big. There could be a lot of objects a lot of morphological objects that this guy can recognize. Hundreds of them, maybe thousands. There's a lot. So the input to this column is kind of limited, but the input to this column is not very limited. That is, now I can now build a compositional model where the input is not coming from the sensor, but it's coming from these other columns. And so I have if I call these objects, these are objects that the lower level has already recognized. Now I have a lot of these objects that I can build in compositional structure. We're here. So now I've started using the language where I'm just going to say all these things. You have one object coming in at a time, and then you have a pooled version of a compositional structure, and then you have an object coming in a compositional structure. In this case, the input may be very limited. In this case, it's not limited, but they're doing the same thing. So my point is, by the very nature of the input to a low-level column, you're going to learn morphological structure. You can't, this low-level column can't learn, oh, I'm going to learn a bicycle, because in order to bicycle, it also needs to know wheels, and then wheels, it can't detect wheels. So it can learn morphological structure, but this guy can learn a bicycle because it's got all these, this guy can learn all these morphological structures, and this guy can then assign them into groupings. So anyway, I'm trying to explain how it is you might unite these, that the same mechanism, depending what you give it as an input, will learn morphological objects or feature to feature, or what we might call feature to feature displacements. So that's the general idea. I'm trying to see if I can get that to work. Did that make any sense? Yeah. Okay. Then the other idea, I was just talking to, we were talking about this yesterday. Oops, that wasn't me. Did I do? That's not me. Somebody else.
No, that was
Ben.
Ben, I think.
Oh, he was trying to show this to the board. When we think about displacements, what's really important is the relative arrangement of things. But it seems clearly that the actual distance between those things can change at times. Like a very rigid object like my coffee cup is not, but clearly I can stretch if I stretch this object and so on, I'll still see it as the coffee cup because all the local feature arrangements are they're not exactly the same distance, but they're in the same arrangement. Imagine you have this tessellated sheet of features. Imagine it's just and you can stretch it. And as long as the features stay in the same relative order position, you kind of view it as the same thing. It's like the t-shirt folding or the logo on the coffee cup wrapping around. It's sort of like that doesn't change the distance, but basically the actual distance between the features is not as important as the relative arrangement of them. And if you change the relative arrangement, you get a different object, right? So I can take a word and I can stretch out the letters a bit and bunch them together a bit, and I won't get confused. But if I change the order of the words, I'm going to get confused. It's not going to be the same word anymore. So all I'm pointing out is that when we learn displacement, somehow it's going to be the displacements are, when we're doing inference, we're somehow able to say, here's these two features next to each other, A and B. They're in the right arrangement, but they're the wrong distance, but that counts, or it counts up to a certain point. You know what I'm saying? It's like, that's okay, I'll still get it. I won't reject this displacement just because A is not the right distance from B.
But as you said, there's a certain point. You cannot stretch everything.
Yeah, right, up to a point, right? If I separate the letters of the word out too much, I just see them as a bunch of letters. Right? But there is quite a bit of, we were talking to Hierarchical this morning about the t-shirt problem and how you recognize a t-shirt, right? In the dark, I pick up a t-shirt and just a pile of cloth. And how do I manipulate that? Well, you move your hand along it to find an edge, and you move along the edge and decide whether you're on the bottom or the top. And what you really want to do is get to the collar. That has a different feel. And then you move your finger along the collar until you get to these. What I do is I get to these 2 points, these 2 seams. They're always sort of a little bit towards the back. And now I know that I'm holding the collar, and I know because the seams are not symmetrically opposites, I know which is front, which is back. So I found these 2 features that I'm stretching out, and I said, okay, now I know where I am on the object. And on shirts, different shirts, it's different. But it's the same method I use. So somehow that works, And the rest of the stuff is the rest of the pocket. If there's a t-shirt on the pocket of a t-shirt has a pocket, the features of the pocket are all relative to each other, even if the pocket's bent or curled, you still see the pocket because all the relative features in the right position. Anyway, now here's the big one that I've been working on. This is like maybe the big opening, and we've talked about this briefly. The original idea behind the model was like, okay, you have a reference frame from the model, and that model has an orientation relative to the body. So you can take a 3-dimensional model and you put it any location in orientation to the body. That would be the clear engineering solution here. And we've found that it seems like that's not what's going on in the brain. And a lot of evidence for that. And I didn't write down all the evidence here, but maybe a few of them. So, so this is the third point. Models have only one orientation dimension, which is vertical. So there's a lot of evidence that we learn models in the vertical, and in particular, one dimension of orientation is has to be correct. And when I gave the example of writing the E and the 3 and the M and the W, it's not like I see the M and the W as the same thing rotated. I just see one as an M and one as a W, and that's it. And it's like, so the models are dependent on which way is up. It's not like there's this independently floating model out in space and I have to figure out its orientation. So there's a lot of evidence for this. So there's an evolutionary argument that when you're walking around the world, trees don't, go upside down. Everything seems to be in the same thing, but you're in different positions. There's the head direction cells. That should be head direction cells argument, E versus 3 argument. And so one idea we passed around in the past, but I think there's a lot of validity to it, is the following. So we have 2 things to do with it. I'm going to argue that the idea I'm working on right now is that we have to have the correct north orientation. It has to be one, but the other rotational orientations don't really matter. And so there's this idea that the thalamus actually is able to compensate for changing in north. So the clearest example of this is that as you walk around the world, your head is always tilting one way or the other. And when you're reading a book, you don't even notice it. but it actually completely changes everything coming into your brain when you tilt the book 10 to 20 degrees. It's just like everything's, I'd have to rotate the reference frames. And you don't seem to do that. And remember the example I gave where I laid in bed, some of it might have been here, but I showed the pictures out my window. And when you're lying in bed, you see this horizontal scene, and my eyes are scanning the scene, but my eyes are actually going up and down because I'm lying in bed. And yet there's no effort in this. And so one of the ideas is that the thalamus actually is designed, one of the things it does is this mechanism we've explored in the thalamus could compensate for this rotation in the vertical orientation. And the vestibular system, the inner ear canals actually feeds into that. And so the brain you could think from an evolutionary point of view, an animal needs to see the world in its upright position and as it's running around. And at any point in time, it may be tilted this way and this way. And the vestibular system says, I know your head is tilted, I'm going to correct it for you. It's not like I'm rotating the model in my head. I'm just rotating the inputs and I'm rotating the motor commands. So, if I need to move horizontally in the scene, basically the thalamus will say, well, I know that given the current orientation, you have to move your eyes this way. So give me the same command and I'll change them for you. So this is, I know it's a little weird, but it seems like this is a reasonably good argument this is happening. So now I can compensate for the vertical in some sense. And if it gets too much, we know that, like if I rotate something around 180 degrees, we know that then your brain has to so slowly rotate it back. It's a mental effort to do this. If I recognize something that's upside down, if it's not clear right away, it takes a linear amount of time to get it to a position where you can actually imagine it. So now the second question is, what about orientation like this? So I say, okay, I'm assuming that I got this coffee cup vertical, but I have all these different views. Wouldn't I have to rotate the model? And in the example, can I borrow that coffee cup? Sorry, not much. So, so imagine we said there's a reference frame for this cup, and the reference frame includes the 3D orientations of the reference frame. So that would mean if I learned this model in this case with the handle on the right, that I'd have to, as I see the handle on the left, I'd have to rotate the model to figure out what the orientation is. I'd have to infer the new orientation. And the idea I'm working on is that you don't do that at all. What happens is, if I think about displacements as always being, imagine, just for the moment, imagine they're always in a two-dimensional arrangement, right? They're always a 2D. And that is, I'm looking at something, I'm looking at some surface or something, and I'm going to calculate the distance to the next thing, but I'm only calculating its sort of a planar angle, not its three-dimensional angle. Then if I look at this coffee cup and I learn the displacements here, I'm looking at the displacements here, and I look at the displacements here, and I can look at the displacements here, and I can look at the displacements here, and so on, I end up with, instead of a three-dimensional model of displacements, I end up with this sheet of displacements. It's not physically a sheet, but that's how you think about it. It's like I'm unraveling the coffee cup in a linear thing. So the displacements would be more like imagine just on the cylinder. You have the cylinder, I'm unrolling it, that, here's what the displacements when the handle's on the left, and here's the displacements when the handle's on the right, and here's the displacement when the handle's not visible. And so when I infer the object, I just have to match the correct displacements. And now what basically I'll be doing is I'm matching some subset of this at any point in time. I don't have to rotate the model. I just have to, this is the model. And I'm just going to like recognize a piece of it and say, yeah, okay, that's the model. And so I'm inferring the model, the object, the coffee cup. At the same time, I'm saying this is what it looks like when the handle's on the left, and this is what it looks like when the handle's on the right. I don't think this is going to take a lot of memory. In fact, it might take less memory to do this. So it's a little bit weird, but remember, I kind of deduced a long time ago that if we're going to wrap an object like the logo around the coffee cup, that the logo has to be sort of a two-dimensional displacement field, and then the coffee cup has its own morphology, and somehow you can wrap it around that. You can put it on a flag, you can put it on a T-shirt, and so you kind of force yourself into thinking about displacements are in two dimensions. And then there's an underlying morphology to the thing. So anyway, so this idea is that in this case there is no orientation to the model. You infer the orientation by just inferring the objects. And once I infer the object, I'm in some part of this model. And I can't see these pieces over here right now. So I don't know. But basically I'm making a series of observations about displacements. And I said, oh, those match the model in this point right here. And if I was looking at a different angle of the object, I'd say, oh, they match this part over here, that kind of thing. So it's a little bit strange, but it gets you around the whole idea that you have to sort of figure out the orient. You do have to get the north, but after that, you kind of think. Now, there are issues with this. I know there are issues with this, but it's very appealing at the moment because it solves a bunch of problems. And then it leads to the suggestion like, well, imagine, I now have a model that represents sort of different, you could almost say this is a model of the coffee cup and this is one state of the cup and this is another state of the cup. It's like, oh, this is the state of the cup when the features are arranged this way. And this is another state of the cup when the features are arranged this way. And again, I don't think this takes a lot of memory. I haven't proven that yet, but I think it doesn't. So then I said to myself, well, could all states of the model be represented somehow in this same basic scheme? Could I think about like the stapler being closed and the stapler being open as, you know, part of a larger sheet here of, in some sense, of a set of displacements where there's different regions that represent the different states of the object. And I haven't worked this through yet, so it's a very fuzzy idea. But it'd be nice, I think about it's nice that you can end up imagining a model of an object where all of its states are representing the same sort of set of displacements. You can't view all those displacements at once, but when you infer the object, you're inferring its state. And so I don't have to have a separate thing that says, oh, this is the stapler, what state is it in? It just says, oh, because I've inferred it in this section of its displacement space, then I know its state. That's just by definition. And then movement of the object would be some sense moving between these regions somehow, like when the stapler opens and closed, I'm going from a bump of activity here representing the stapler in a closed state, and over here a bunch of activity open in the open state. I don't know if this is going to work, but that's what I'm thinking about. So this is displacements are 2D arranged like a sheet. And all displacements we thought of lying on a 2D sheet, different views of an object that represent different regions of the sheet. Inferring a cup with a handle on the left versus the handle on the right does not require determining the orientation of the cup. So both views are stored in the model.
So what about the non-spatial features?
Like what?
Like color?
Oh, I told you I didn't want to talk about that yet. The way, I mean, I think I'd go back to the way we were thinking of the graphs earlier. You can associate with, imagine there's some, you're at some point in the object and you can link from that point to other objects and maybe feature, you know, like even maybe something like color. I don't know yet, but the point is you could say, oh, somehow I have to get like, okay, somehow the mental logo is only visible on one of these things here. So, you know, it's sort of continuous until it disappears and continues. So it's only located, and yet somehow the logo has color associated with it, right? So at some point you'd say, oh, there's this, at this point, this is the letter N, and or this is the word Nementa, and I have a link to that over here. So I can't put it in this model, I have to link to it. And so I somehow link to the color, or I somehow link the underlying morphology and shape of this object is not completely dependent on the color. So if I know the color, I might isolate where I am, but if I don't know the color, I still can infer it.
Well, if you as soon as a set of attributes out there, and that let's say, for argument's sake, that you have this thing that you're perceiving in front of you of a model, and maybe it matches in some of those attributes, but not all the others. So you've got something, so the recognition would be it's similar.
Yeah.
At some point, you would say it matches in all the things I know about, so now I have identity.
Yeah, right. Yeah.
So it gives you a soft way of associating things from the most important aspects of whatever is being stored in the two-dimensional map.
Yeah, yeah. No, I think that's right. I think that's right. I would agree with that.
So the attribute is going to be part of that state now.
It would be, I think the attribute is not critical, right? It's like, the
Like, look at the
displacement,
ceiling, I have like lights on and lights off. Those are different states of the light.
because that's not a light, that's
That is, some of them are broken. That's it, some of them are broken.
okay,
And like once, the same light, they have different state. One is on and one is off.
yeah,
There's no color in there, just a luminosity or something.
Yeah.
Some other attribute that
Well-
represent that light is on, light is off.
well, it's interesting, I think many models of the world, it's interesting, I'm hearing you talk about this, Liz, and I'd say my model of this room doesn't include what the lights look like or where they are, or which ones are on. If you ask me to like draw a map of where the lights are in this room,
But if I tell you how do you represent that camera is on, the camera is off, there's an LED there at the time.
fine, okay, fine.
That's an example.
Yeah, my point is, you have this sort of, and this is just like we talked about the graph. The graph represents, in some sense, the shape of the object, right? And and then you can link to the specific things that might be associated with that point. Like you can link to the color, or you could link to the mug. The actual mug would link to the logo. The logo wouldn't be part of the, because we already learned that separately. So I think what Kevin's saying, you can still infer the shape here independent of this, but if you do know this, it can help you if you've learned that. My point with the lights in the room, I haven't learned what the lights look like or which ones are on and which ones are off. So looking at the lights doesn't help me identify the room. But if I study the lights every day and I go, okay, what kind of lights are in here? I'm a lighting guy. Okay, I've got to memorize. The next time I'm looking at a room, I go, oh, I know this room, but most of it, I wouldn't do that normally, right? It's too much memory for me. I'm not going to think about it. So my point is that these links are, you can temporarily look at what's associated with some place here, but you may not remember it. I'm not sure if I'm addressing your comment. I'm just pointing out.
I'm just like, agreeing with Kevin that there's actual attributes to the location that will help.
Some things are really helpful. I'm just thinking the lights for me wouldn't be helpful in my case, right? Because I just haven't learned it, but the arrangement of those two screens and these windows, yeah, that would be, that's what I would use.
I also think that if the main thing is to recognize where you are, recognize that you're in the same room at the time, then you just need to know a sufficient number of attributes of the room for your perception to say, I know that I'm in the same room or not. I don't have to memorize every detail of the room.
Right.
But if I have spent my life as a lighting engineer, I might take in other attributes just because of the fact that I'm geared to add those attributes.
Well, I've used the example of my sailboat, right? I have a sailboat and I know every little detail of that sailboat. You'd walk up and you wouldn't know those things. You just say, oh, kind of sailboat.
And we even have names for this.
So yeah, so to me, I'm like, I would see like, oh, someone left this little clip on the wrong orientation. I'd see that, and you wouldn't know that. So it just depends on how much time you spend looking at it and playing with it. And I've spent time calling all other things. I know every little thing. And therefore, my model of the boat is very rich, and yours would be very modest. And just because I spend a lot of time at it, anyone can do that.
But I think you say a certain level at which you say it's sufficient for me to operate on. I mean, bombarded by images all the time.
Yeah, right.
But if something comes on up that I say I need to observe something more, like I've been keyed, someone says I'm looking for this book, I might, hone in on something like that. So I think it's a flexible.
Yeah, I think right. I agree with that. So I think I've covered all these points here. I'm trying to understand object behaviors in this idea of a single sort of model, and that what you're doing is instead of having a model of what an object looks like, and then sort of a separate. I mean, it's not like our old views of displaced behaviors are wrong. Let's just have a different mental model for it now. That in some sense I have these memories of all these different displacement, but all these different, sometimes I can memorize the views of an object in its different states as actually what I observed looking cleaner at this thing in terms of its displacement. And as I manipulate the object, I'm looking at different parts. So somehow there's this continuation between, again, I'll just say it one more time. The object, the cup with the handle on the right and the cup with the handle on the left are really the same object, two states. And similarly, then I might be able to do multiple states of the object in terms of its deformations and morphology or changes in its features. that that I would say, oh, okay, now I know it. That's all I can. That's all I'm trying to do. Yeah. And I'm trying to prove myself that a two-dimensional displacement, and that is displacements that really are primarily two-dimensional, would work. That's not so obvious either. So, anyway, I
Ask a couple questions.
yeah. So again, just a reminder, I'm not done with this. I don't really know if anything is going to work.
Yeah, I just think it's such a fascinating idea that I want to dig into it a little bit.
Okay.
Okay, so one question would be, where would a model like this live? Like, what neurons would be responsible for this 2D sheet?
It's pretty simple. Again, I talked about earlier how you could feed displacements into the temporal memory. So instead of putting in a spatial, imagine what you're representing in the mini columns is, let's say local curvature at that point, right? And so what it's in, then I haven't worked through the details, right? But the basic idea, all of this could be represented in this sheet of displacements could all be represented in a single layer of temporal memory. It doesn't have to be spread out. It's just, at any point in time, you say, I know where I am, and at this point in the model, these are the displacements I should see, and then because it's a highly unique representation. And then you go, okay. And so, but if you fed in displacements into the mini column structure, so the system is representing displacements, and I'm feeding in as context the unique location on the object, then I can say in a unique location in the object, this displacement is represented, uniquely so, and therefore I can link displacements. I can say, okay, at point A on the coffee cup, there is a curvature to the right here, let's say. That's, go this way and it curves this amount. On another object on point A, it would go a different way. So if I have the unique object and I have the displacement, then I can learn the transitions of displacements like I learned the transitions of notes in a melody. And it could be unique for the object. If I didn't have a unique representation of the object, if I said, well, there could be two different objects, then I might say, well, at this location, if I move to the right, I'll get one displacement. If I move to the right, I get a different displacement on object A and a different displacement. Then as soon as I move, I know which one it is. It's the same way the temporal memory winnows down from notes. It would winnow down a series of displacements associated with locations.
So the 2D sheet, the same 2D sheet here can actually represent multiple objects, and in fact, multiple objects simultaneously.
Yeah. It's very much like we did in the Columns Plus paper. There we were feeding in a unique representation location as context, but we were using features, observed features as the input to the temporal memory, right? Here I'm going to say switch out features and put in displacements, observed displacements, and then you basically get the same thing. Now it's invariant to the Now it's invariant to the, it's just different, and it'll narrow down things.
In this representation, we were still specific to a specific scale of the object. It's to be very specific.
Well, all right. So I already mentioned that scale is a problem, right? So we don't want it to be right. So
how about
well, scale in this case? What is scale in this case? Scale in this case says, let's imagine we're just talking about curvature, okay? And we're going around the cylinder, and the cylinders can be bigger or smaller. The scale would say, okay, when I move in this direction, I should feel it rotating away from me this way. Not like this way, but this way, right? If I go this way, it's straight. If I go this way, it's curved. So that's my prediction. Now, my prediction says, maybe if I consider the distance fixed, then I expect a very specific curvature. What if I get a sharper curvature or less? I need to say, oh, that's not the right curvature, but it's in the right direction, something like that, right? And so, because then I say, oh, well, it's a tighter curve than I expect, but it continues to be a tighter curve. And then somehow I have to say, oh, this is a different scale.
Yeah, I'm wondering if you can infer the scale sort of on the fly.
I think so.
Based on the amount of motion and based on my model, you say like, oh, moving this much only moved me this far on the object. Oh, it's the same thing, but it just means
yeah,
the object
I think it
bigger.
is. I mean, it's complicated because what if I had unique objects that were different scales in that size, right? I wouldn't want to confuse them.
Yeah, but I also want to recognize how the cups are not just different in scale but deformed.
Okay, well, I think the hope would be that as you locally, you always have the sort of same displacements, and yet the the scale and deformation is that, okay, the distance traveled is somehow changing, right? It's like it's sharper or less sharp. But as soon as it starts going the wrong way completely, then it's not a
I
scale
also think
issue.
about it along this line that like locally sort of roughly the same. And it's so how would I represent it this way? So since I don't know exactly where I am on the object, at least initially, so I represent it as an input. I have some local curvature here, and I have a displacement in a certain direction. It's just going over there.
Yeah.
Like imagine in a 2D sheet, just going in a certain direction. And I observe another local curvature at this point. So I have a sequence, a spatial sequence of those local curvatures.
Yeah, right.
And those recognize the object without.
But somehow the actual specific differences matter too, because I would know if this is the one I had before. I know the difference between a little pneumatic coffee cup and the regular pneumatic coffee. So I don't have to say, oh, I adjusted, it's a coffee cup, right? No, I said, no, this one's a small one. So that tells you it's kind of an Uber parameter, right? It's like, it's something that the model, inferring the model says, yes, I recognize this shape, but by the way, it is not the right dimension. So it's not the dimensions I learned it in. So the model has to include those dimensions because I learned the specific coffee cup, right? So that's got to be part of that. But then I'm able to infer it even though it's not the right curvature. It's not as steep. So one way to think about this is to say, okay, if I can recognize everything just like I observed it, it'd be a perfect match. But if things aren't I observe it, I'm able to still keep going, even the fact that the distances are wrong, right? Mm-hmm. And at some point you would say, okay, they're all wrong by the same amount. Therefore, like just a smaller version of the cup, or maybe, you know, I don't know yet, right? Mm-hmm. But I think it can work.
Or maybe there's some cards which just go by the rough direction, right, without taking the location into account, and then you would recognize, oh, this is a coffee cup or a species of the family of coffee cups, and then there may be others which should take into account really once I figure out, oh, I'm looking at the coffee cup, to take into account.
Well, maybe I'd rather have one column do everything, right? I mean, maybe that's. I mean, the evidence we would have would suggest that columns are columns. They're not different in that regard. But
they're different regard to input.
Well, yeah, they have different input. But you know, going back to imagine just roughly, imagine this is a grid cell module here, and so this is a bump representing location in space, and these actual cells are unique to any particular object, right? That location on a particular object. And then imagine you have another set of cells here that is taking in displacements. And the same idea, there's many columns here, but individual cells say, okay, here's a displacement in the context of a particular location on a particular object. So imagine that this feeds into this, and this feeds back to this. So your movement, you're saying, I know how I'm moving, and so and I know what I'm detecting for my displacement. So if I start narrowing down here, I'll start narrowing down here, and if I and then when I narrow down here, make different predictions about this. And it's just hand-wavy, but this is the basic idea I'm working on, is that you can be modeling. This temporal memory layer basically says, give me something that is not, give me an input which is not unique to this object, but I can detect and determine, and and then in the right context, I'll make it unique. And so then they can feed into each other. So, you know, at one point I'm getting the displacement, and next year I'm getting the path integration from grid cells. And so these could interact back and forth, and you basically narrow it down to, you know, where you are and what, you know, then you can predict what the displacement will be the next. Because these patterns would link to each other. Well, they could link to each other, but they're linked to these things, basically, for certain. Anyway, it's a very rough idea here, but the way I think about it is the temporal memory layer gives something you can measure that's not unique, and can form a unique representation of it. And then if you have multiple ones that are working on different sort of inputs, So, one's detecting this and the other one's detecting this, then together they narrow down the answer. And you can even think of the temporal Pooler layer as an extension of that. You can think of the temporal Pooler layer we haven't hypothesized it works on the Minicom idea. But the temporal Pooler layer says, I have a union of ideas here. This is all the different objects I could be looking at. But then you have these inputs from other columns that is sort of another context that says, oh, well, given the context of these other inputs, I can narrow this down. And then you could basically, since you narrow this down, then you could feed this back down here and say, okay, well, my neighbors told me it can't be those things, therefore I'm going to tell you it can't be those things, and you can't really do this. So somehow there's this balance between these things that are sort of narrowing down as you move and narrowing down as you get input from other sensors. That seems to be the basic idea.
There's one perception also that I think is interesting. I think it's slightly at a higher level than we're discussing. And that is, if you come into the room and someone's broken off the two pieces of the stapler and they're sitting on the table,
Yeah.
you instantly recognize broken.
Yeah.
If there's an object that you come into a room that you've never seen before, and you see something that's all kind of part of the object, and then a divot in it, and then a thing lying on the floor, you instantly come up with broken. So
I'm saying it was a novel object? How would I know it's broken?
But you connected the fact that I see two objects, they matching color, whatnot. I can match, okay, that thing came from here. You very quickly can recognize, you could recognize, something's broken.
I'm not sure I would agree with your second point. The first point I agree with.
Okay.
If it's truly a novel thing, truly novel,
Right.
like it's not like anything else I've seen before, I don't think I would know that it was broken. If I see something that's kind of like, oh, well, it's kind of like a cup in some two parts. So what I think is going on there, Kevin, would be like, imagine the big sheet I erased, right?
Mhm.
And you can infer you might infer like the bottom of the stapler would be part of that sheet.
Mhm.
And then as you move, you would expect to see the top of the stapler, but it's not there.
Right.
And then you'd see another thing down here, you'd see the top of the stapler, and that's part of the sheet, but then you realize the bottom is missing. So then you say, at some point you say, well, there's something wrong here. It's missing these components,
They're
right?
supposed to be connected, but they're not.
Well, they're supposed to, I should predict this is there and it's not there,
Right.
right?
And so I look for where.
I don't know, like, if you walk in the room and you saw the top of the stapler, that's all I saw. I'd say, well, that's the top of a stapler, right? And I would say it's missing the other half. The model could explain that, right? It says, yep, I recognize that's part of the stapler, but I'm missing the other part. I'm expecting it should be there. In either a closed or open state, it should be there. I don't see it. That's one problem. I think I could explain how that happens. Now, piecing together the fact I see a top of the stapler here and a bottom of the stapler down there, that seems like maybe a more of an uber higher level cognitive.
Yeah, that's why I said it might be
problem.
a higher level.
Yeah, like putting two and two together, that belongs to that, and they got broken.
Right.
I don't know.
But I'm saying your chaining of things together has the potential for maybe handling this more abstract thing.
Well, I think it definitely has the ability to handle like, oh, I'm missing a part of this thing, or this thing is broken, or this thing is bent out of shape, and it doesn't, things like that. Yeah, it would do that. It would, yeah, and I suppose if I break something, imagine I take the coffee cup and I break it, two pieces. Well, in some sense, the broken edge is a feature of that object now, and we can see it doesn't belong there. And I might even recognize it as, oh, I know what broken ceramic looks like.
Yeah.
So that's getting beyond my thinking right now. I'm just trying to figure out how do we recognize, coffee cup. And
Yeah,
stapler.
but I'm saying that what the mechanisms you propose, could, I think, be extended into that.
I think you're right. Yeah, I mean that's the hope, at least, right? The hope is you get to the core idea about how models are built, even if you have a lot of the details wrong. The core idea about how models are built and how they're inferred. Then, if you get that right, then you can sort of tweak the ideas of it and figure out all these other things, right? But these ideas I'm working on here are very odd. I wouldn't have predicted this a while ago. This idea of this two-dimensional displacement sheet and wrapping around morphology. I mean, all this stuff is, or even the idea that there's only one orientation that matters, vertical, and the others are not represented. not represented externally explicitly, they're represented in the model itself. My point is, if I can get this all to work, then it seems like, oh, that's a whole new base in which to start tweaking it and figuring out other things. Because if this is wrong, then I have to start back to scratch again.
Yeah, but I mean, it also makes it simpler in the fact that however you want to look at the retina, it is primarily getting a two-dimensional perception that, and that makes it a lot easier rather than having to infer 3D.
This has been one of the big bugaboos all through the beginning, right? The cortex is two-dimensional structure.
Right.
The sensory organs are two-dimensional, and yet we're building these 3D models. We have to represent them somehow. There's an entire question even about grid cells, whether they can represent 3 dimensions or not. And Marcus and I went over some papers with that recently, and it's questionable. Maybe yes, maybe no. And so it'd be kind of cool to come up with a way of modeling things using 2-dimensional structures that capture 3-dimensional shape. That would seem to be a really nice result.
I mean, there's concepts you've heard us talk about self-organized maps, stuff like that. And you look at, where the for binocular vision, where the deeply intertwingled two halves of the vision.
Is that a word, twinkled?
Huh?
Is that a word, twinkled?
Okay.
I was just joking. It sounds like a fun word. Twinkled.
Okay, but that was, taking something that was higher dimensional and forcing it into a planar configuration. And that's what you.
The self-organizing maps do that?
Yeah.
Yeah.
And so the same thing.
Oh, yeah, I get it. Yeah.
When you get the pinwheels of the orientation in there, that's again a multidimensional signal that's being compressed into a planar representation.
Yeah.
So the power of self-organizing maps, which I would maybe argue is happening in the cortex, is that you get these multidimensional inputs. They have a signature of some sort, but it looks really weird being imprinted on there.
Yeah.
And,
I read that a long time ago. Was that Cahonen who did that?
yeah.
Yeah. So do I need to read that again?
Either that or I could.
No. I mean, the question is it really important that I have the general idea. You're collapsing these structures onto 2D surfaces.
Right.
But do I need to know more details on that?
Yeah, but if you look at the way that you build it, basically there's a gradual process where you move these things closer and closer to each other using some kind of metric that these things are similar to each other.
Yeah.
So to me, that's a very
it's not clear to me that we're collapsing 3D structure on the 2D surfaces. The whole idea here, the displacement thing
I'm
is
saying some higher dimensional thing, some other attribute.
Well, there's different ways you could do that, right? Like the whole idea of the displacements being really sort of in 2D gets around that, and then you can link from any point to some other object or some other thing.
Yeah.
It's not clear to me that concept of collapsing on these onto a surface is the right metaphor. I'm not sure.
Okay, I think it's different, right? Because what they do with the self-organizing map is dimensionality reduction.
Right.
Which we don't want to do here. It's not dimensional reduction. We still represent all the different states of the object, like rotation or opening, closing of the stapler.
Right.
We still represent all the different possibilities.
Right, but in terms of, if you look at dimensionality as being the attributes, and that you have and that the ability to, I'm trying to pick the right word, localize the detection of that attribute, whether it's orientation, whether it's, which kind of winds up in a pinwheel on the thing, whether it's this thing that where the two halves of visual fields are put close to each other. Those are there's a morphology there of the cortex itself that is suggestive of the fact that you're putting multiple dimensions. I mean, I don't believe that the only thing that those columns are doing is just doing orientation. It's just that when you look for it, you see that particular pattern come on up. They're probably doing a lot more.
Yeah, I think the orientation is completely wrong, by the way. It's almost completely wrong, if I can explain why. Figure one. All right, I think it's an interesting observation with self-organizing maps. I'm not sure yet if it's the right metaphor for me to work on right now, or maybe one thing about more. But I think what Heiko is saying is we're really not trying to do dimensionality reduction. We're just I'm trying to sometimes finesse the 3D structure by learning 2D curvature, 2D points of curvature.
Oh, yeah, the way like Marcus and Mirko, that's a completely different way of representing high dimensional stuff.
Yes.
There are lots of different.
Well, they have
3D
lots of
things,
different grid
and
cells.
Yeah, each one has a preferred direction,
Yeah.
and you project everything according to that, and
Yeah.
you have a bunch of these, and together they represent the full.
I don't know if that
3D.
principle could apply here. It's interesting question. I mean, I don't
It's a
like.
pretty generic principle.
But the idea that I have to be able to make these projections onto different planes. I don't know how that would happen here.
I mean, that's just the proximal synapses do that. It's just a vector dot product.
That's so confusing. I mean, the basic principle they laid out there is sort of an extension of the principle we had in the columns plus paper, which is in the frameworks paper, which is you have multiple modules representing the same thing, and together they represent a rich representation.
Yeah.
We did it in two-dimensional sheet, two-dimensional plane. They're doing it now. These are representing different slices in three-dimensional space.
Yeah.
Right? Same basic idea there.
Yeah, there'd be like a preferred, maybe you have a group of cells that has a preferred direction,
Yeah.
and then another group of cells has another preferred
Yeah.
direction.
I mean,
It doesn't have to be grid cells. It can
Yeah.
be anything.
I mean, sometimes the temporal memory is an alternate way of doing the exact same thing. It's like, is it?
Yeah, no, you have another way.
Yeah, so I'm more comfortable with that one. I feel like that's pretty certain that's going on to some extent.
That's how we did the Nick stuff.
Okay, I always can't remember what that
Yeah,
was.
but basically you could do these multi-dimensional mappings with the temporal
Should I
memory.
read that again?
Well, it was just a demo.
It was a hackathon thing.
That's a good word.
I mean, it can map anything to anything, the temporal memory, so you can just learn all these different maps.
Fast, like I
Inside.
interact with the location.
Yeah.
In some sense, this is kind of where the granularity of locality and where this is represented. I mean, it could be way down deep, as you're saying, with many columns, or you could organize at a larger level, you know, but I don't know where the granularity actually is. I mean, I'm just trying to fit the data that, you know, I've read to what is there. But it is an interesting notion is how distributed is it, how localized it could be.
Well, the theory is that everything has to happen within a single cortical column. So all of these
We're kind of
things,
relaxing that a little bit.
Well, I'm relaxing in a couple ways. One is if we start thinking of compositional objects, you might have to relax that.
yeah, but that doesn't mean the entire sheet is involved. And that's what the level, the Clone maps are pretty much at that level.
Okay, well, you know, like I said, there could be a granularity boundary here that, you know, I can't put right now.
You know, talking about granularity, here's another interesting idea. Can I change the topic?
Sure.
You know, the weird thing about like V1 just gets input from the retina. Or any prime, S1 gets input from the retina. But V2,
Yeah.
well, okay,
Yeah.
okay.
That's okay.
That was the rotation. But now V2 gets input from the retina and from V1. Both of the layer 4. It's like in other layers too. And that's the general rule. You go V4, which is next after V2, is, you know, it gets input from V1 and V2 and from the retina. It's like, oh, how do you make sense of this? Like, you know, so one thing I asked myself, like, well, what if I was trying to learn the coffee cup? Or to say, this is one very specific. I have a cylinder and I'm trying to put the logo on it. Where would those representations be? One could argue that V2 might be saying, I'm observing the larger object, which is the cylinder. It's a morphological object, but I'm being told there's features that are being detected in V1, which is the logo. And therefore, it sort of flips it around, like the unspecific morphological object might be represented in V2 in this case, and the specific, like, this is the logo, or this is the word, or whatever it is in V1. And so V1 is saying, you're determining the morphology, but this is the feature that you should associate with that point on this morphology. it kind of flipped it around a little bit. I used to think like, oh, well, you have this morphological stuff low down and first region, and then I'm just pointing out that that's an interesting twist to ask yourself as I figure out how to do these compositional objects. What if it's involving multiple regions in a hierarchy? Who's representing what, and what are the links between those two? I know in the past I've always argued we shouldn't do this, but now we shouldn't be thinking about hierarchy. But I think I've got it.
And we also have all those feedback links that are going downwards.
Oh yeah, but that's the point, right? There's a huge amount of linkage both ways.
Yeah.
Yeah.
So that would argue something is trying to reconcile with something.
Yeah, well, or it basically, it's not reconciling as much as it might be just forming links between the features, right? The morphological object in V2 would say, or your second region, whether it's S2 or whatever, is saying, okay, I'm on this point on the surface of the cylinder, and I'm just going to associate that point with what you're representing down there in region 1. And so you're saying there's a logo here. Fine, okay. So I'm just going to, when at this location, I'm predicting you should be seeing a logo. So it's telling V1, and then V1 would be saying, well, I'm seeing a logo. It should inform you what overall object you're doing.
Yeah, I think that's the key word. One layer informs to our layer.
That looked on lunch
Yeah.
meetings.
Okay, time's up. We can continue talking.